So we left off last time talking about climate change, and we said, is this not working anymore? We said that there are potentially huge implications regarding biodiversity, and that we are moved into the Anthropocene as a new geologic age. And so we talked about this beech tree, and we talked about the previous range, the future range, and the overlap. In terms of what we this is kind of where we left things. What we need to do. This is the stuff that you all know about. This is the stuff you're bombarded with every day, right? What should we do? How should we be fair to developed and to industrializing nations? And how should we move forward? And again, I will point you to the sort of meter of things. Yes, it's happening, but that's not necessarily a doomsday scenario. It's still very much in our hands. And do you want all the glaciers to melt or 3/4 of them? So we have to get together, as this is a global environmental problem, as a world, and implement a global solution. And historically, the United States has been a little bit unconscionable with regards to our role in this. At the time of the Kyoto Protocol, we were the only developed country that did not sign on to the Kyoto Protocol, which simply called for a reduction of greenhouse gases by a small amount. And we said, our administrator, or our, let's see, where's my notes about it, right? So there were 2,200 delegates that met in Kyoto, and there were 38 developed countries, all except the United States, signed on and said that we would cut the greenhouse gases that we talked about by 5%. And the United States didn't sign on, so this is really tough because we were at the time the biggest greenhouse gas contributor, and we were only 4.6% of the global population. So we were most of the gases, very small amount of the population, and so historically we've not done a great job. All eyes are on Paris this year, and this is kind of beyond the scope of this class, but we are all convening again as a world in Paris in December to look at a binding, economically driven model similar to cap and trade, looking at how can we as a world be fair to industrializing and to industrialized nations and lower carbon dioxide. Our administration now in the United States has also been really good, despite a lot of roadblocks, at addressing this. So this is something that, again, is very much in our hands, and it is worth looking at in detail as you go forward after class. One note is that we predict the future when we're talking about climate change through, funny, the same acronym holds true for two phrases rather, general circulation models or global climate models. And this is a dangerous game. And I say this because when I was doing my PhD research, I was a mathematical modeler of environmental systems and sometimes still am. And there are certain rules that you can't get around when you're talking about modeling an environmental system mathematically. These models are essentially gigantic mathematical algorithms with equations that mimic every aspect of what goes on Earth, from how much ash and soot come out of volcanoes, to how much coal China burns, to how much the phytoplankton in the ocean take up carbon dioxide. So it's a dizzying array of a number of mathematical equations. And the way that you predicted the future using mathematical modeling is to have a complete set of data that you can put into your model, every aspect of it, and then you run it forward. You hold some data out that's sort of, so you do it till the year 2000. You hold the next 15 years of data out, you run the model based on data through the year 2000, and then you see how well it predicted the future, because you actually have that data. That's called calibration. And when you calibrate the model using an amount of data that you held out, you see how sure you can be about your model. And then you can, the other cardinal rule of modeling is for every 4 time steps of data you have in the model, you can walk forward 1 time step. So what that means is that if you have 25, I'll say 20 round, 20 years of data that's put into your model, and some of these mathematical equations we've only been collecting data on for about 20 years, you can only walk forward 5 years. These models are only allowed to tell you what's going to happen in 2020. But we run these models out and we say, this is what's going to happen in 2100. This is what's going to happen in 2050. You can't do that. It is sort of rule number one of mathematical modeling. Then why do we do it? Well, it's a global situation. It's a global problem. There's no testing we can do. This is an experiment that is unfolding before our eyes. So it's the best we can do, but I wouldn't even call it a science, what goes on with these mathematical models. I'd call it an art. You're sort of trying to figure out something, breaking every rule that is set forth in mathematical modeling. The other danger here is that these mathematical models have gotten really slick, right? Maybe you've seen some online, maybe you've seen some in documentaries. If you watch things, they show time changes and all over the place and all sorts of glacier melting and temperature rising. And they interface the math with these beautiful high-tech software packages. And the danger there is that they lure the public into thinking this is true science. This is absolutely what's going to happen, because you see these images and you hear people saying, this is based on data, this is based on science. And you know what, I'm here to tell you it's not. It's really kind of crap stuff we do. So you should take these models really with a grain of salt. And again, why do we do it? Well, because we don't have any other way of predicting the future. You can get the environmental sort of extremist saying, oh gosh, everything is going to be over in 5 years, and you can get people who, maybe work for the coal industry that say, look, everything's going to be fine. So lots and lots of models are made, and they're really, really difficult to believe. This is a picture of models, kind of lots of different models that different people, different organizations have done, and this is maybe a more plausible way of looking at it. The yellow line here is an envelope of predictions. And the predictions right now say that there will be a change in global temperature in degrees Celsius from anywhere of 1 to 3.5 degrees by 2100. Again, not great science, it's more of an art, but this is the range. And I remember when George Bush was president, I always have to throw out the caveat, not political. He said, when these models were coming out, he said, we shouldn't worry about climate change. I woke up in D.C. and I came down to, I think he went down to one of the Carolinas, and that temperature changed 3.5 degrees Celsius on my trip, and I didn't die. So it sort of, shows a lack of understanding of the science, right? And then you hear about people throwing snowballs on the floor of Congress. It shows a lack of understanding of the fact that, again, some places are going to get warmer. Remember we said Alaska has gotten about 10 degrees hotter locally, and some places will get colder. So a degree or two has global consequences. And these positive feedback mechanisms, that's kind of what we talked about at the end of class, right? So 2 people came up and asked me about that. Positive feedback simply means that the hotter it gets, the hotter it's going to get, right? So sea ice. Sea ice reflects the sun back into space. If you melt sea ice, anything that used to be sea ice and is now either ocean or land will not reflect it back into space. So you'll trap more rays, so it will become hotter in the atmosphere, so you'll melt more sea ice, which will trap more rays, which will make it hotter, which will melt more sea ice. So it's a positive feedback mechanism. I don't mean to say that this is the only thing that happens. There are also a lot of negative feedback mechanisms, and we'll look at this when we look at techno-fixes. Our brilliant, not really, ideas about how we can engineer the atmosphere. It's petrifying to me. So if you have the planet warming and you have more rays coming in and being trapped, a negative feedback mechanism, this is sort of like homeostasis of the planet, is that you evaporate much more seawater. And where does the seawater go when it's evaporated? What does it become? Clouds, right? Yeah. So you have clouds in the atmosphere. That acts the same way as sea ice, where suddenly the rays will preferentially bounce off into space. So the cloudier it is on Earth, the fewer the rays will come in. So that's a negative feedback mechanism. We like those. Those make things more stable. So it gets hot, more clouds, more sun's rays bouncing off, and it cools. So there are those as well. But the bottom line here is that we don't know. We don't know, and we have to find out. We'll look at techno-fixes Oh dear, I think I put it in the wrong thing. We'll look at techno fixes, or at least I can tell you about them. This I liken to the problem of obesity in the United States, right? When you go and turn on the TV, when you read the news, when you read magazines, you're bombarded with weight loss pills, potions, shakes, this, that, right? Our country and the pharmaceutical industry is trying to trick you into thinking, oh, if you want to stay really thin, you can still eat everything you want. Just take this pill and you'll stay really thin without exercising and without eating less. And that's what we're trying to do now, it seems, with climate change. People want to come up with engineered solutions so that we can keep the status quo, so that we can keep burning coal, oil, and natural gas, so that we can keep going on with our broken agro-business in this country and elsewhere. But the thing is, the solutions to climate change are quite simple. And the solutions to climate change are everything we talked about in this class. So this is a picture that shows, and you have these slides, that shows what can you do to prevent future climate change, right? It's here, it's happening, but how can we prevent it from getting worse? The answers, as you can see here, are simple. Our last topic in this whole class, sniff, sniff, it's over, our population growth, right? We started out talking about the more people, the more resources used, the more resources used, the more pollution generated. So if we rein in population that's currently experiencing exponential increase, then that will prevent future climate change. We talked about agriculture, and those two bottom things here, reducing deforestation, the power of trees to suck carbon dioxide out of the atmosphere, and practicing sustainable agriculture. Who knows what that is? I don't know what that is, right? This is something that I'm trying to just give you the tools to figure out what you think it is. Does genetic modification have a place in this? Does it not? Should we return to organic methods? Should we try to develop a next generation ideal pesticide? So this word sustainable agriculture, you have to figure that out for yourself. But there are ways of doing things, we looked at king corn, that harm the planet, everything we're doing now pretty much, and there are ways that will stop climate change, reverse climate change through the food that we eat. So those are initiatives that we should be looking at. And then also those, the top three all are fossil fuels. And recall fossil fuels, we talked about them in and of themselves, but they're prevalent in the agricultural industry. They're prevalent in materials, minerals, mining, waste. It's everywhere. So we have got to figure out our energy future. And one of the things that it has to keep in mind is the fact that the planet is irrevocably warming right now. So can we move to alternative energy technologies? Again, you have to figure this out. Are you a believer in carbon sequestration? What that is essentially, I won't get into it too much, but vacuum cleaners that suck carbon dioxide out of the atmosphere, turn it into a solid form, and inject it down into the subsurface. There's some initiatives that are looking at actually sucking carbon dioxide out of the atmosphere, making essentially marble or limestone, and building sustainable buildings with it. So you're solving climate change and you're having recyclable, renewable materials. So to what degree do you think technology should play a role in sustainable energy, getting carbon dioxide out, and to what degree should we return to sort of older methods? And then cleanup. Once it's there, once it's been created, there are things we can do. Looking at taking carbon dioxide out of smokestacks. It's really, really difficult abiotically, but I think I mentioned this in this class. People are looking at algal biobags now. It's a really, really neat concept. If you're interested, you can look on YouTube. Neil deGrasse Tyson has a NOVA special, Science Now, and it's like a little 15-minute clip that shows these algal biobags. You have these plastic permeable, semi-permeable bags that are filled with water and a little bit of nitrate and a little bit of microalgae. You hang them in the smokestacks. They suck all the carbon dioxide out of the exhaust, which is profoundly expensive when you're talking about doing it abiotically, like engineering a system. And then you can take that algae, you can feed it to cattle, you can turn it into biofuel. So it's solving a problem and then creating a valuable raw material. So things like that, taking carbon dioxide out of smokestacks and then planting and tending trees. This is the sort of eat less and exercise situation. However, there is, sorry, I may have to Yeah, these slides are on. If you're interested in cap and trade, have a look at that. The slides are online. I won't get into it, but I want to show you on another slide there we go. The thing that people are saying to do, that's why I couldn't figure out my slide. The thing that people are saying to do instead of the sort of eat less and exercise model, there's a sort of conceptual diagram of carbon sequestration, taking carbon dioxide out, making it into new things. Techno-fixes. Scientists have suggested, for example, launching helium balloons into the geosynchronous orbit. That would work the same way as clouds. You have billions of helium balloons in the upper atmosphere, and the sun's rays will bounce off them. Also, giant mirrors up in space, so that the sun's rays will preferentially be bounced off into space. Sulfate cannonballs, launching huge amounts of sulfate cannonballs up into our atmosphere, the troposphere, to make our atmosphere hazy and cloudy. And that will bounce the rays back into space. Also, these giant seawater platforms. So you have these platforms in the ocean, and they suck seawater up out of the ocean and spray it into the atmosphere. Again, the principle of clouds. Some have noted that iron is a limiting agent to microalgal growth in the ocean. So why don't we dump a whole bunch of iron into the ocean, and that would cause the algae to increase their uptake of carbon dioxide through photosynthesis. And some studies show that in order to offset all of the carbon dioxide we humans have put into the atmosphere, you only need to get the algae to increase their uptake by 1/100%. So not very much. So this is stuff that goes on, that people are thinking of these global solutions. Also, some things are sort of handing the keys over to you. You have to figure out what you think of this. Personally, it petrifies me, because what if there are unintended consequences, right? What if launching these helium foil balloons causes something more catastrophic than climate change? This is a good way to kind of start shifting over to ozone thinning, right? We thought we were doing the right thing with ozone depleting compounds, with chlorofluorocarbons, and we ruined the ozone layer. We thought we were doing something good. So again, it's up to you guys to figure this out. So those are some of the techno fixes: helium foil balloons, sulfate cannonballs, iron in the ocean. Tough. Last note before we move to ozone thinning, and that is, I just wanted to sort of give a nod to this whole notion of, is it happening or is it not? Because it's crazy to me, but you still hear people saying, we're not even sure it's happening. And the funny thing is, as someone who, I wrote about climate change a million years ago, 1999, I got my doctorate, and I was looking at this. I was looking at the role of vast circumboreal wetlands in climate change. Are these wetlands a sink for carbon dioxide? Because they're constant plant accumulation, and plants need carbon dioxide to photosynthesize. But as you know, with wetlands, underneath, the plants are starting to decay in groundwater, which is anaerobic. So they're also putting out vast quantities of methane. It's crazy. I just tried this when we first got there. I landed in a helicopter in the middle of this huge wetland, and I took a piezometer and stuck it down in, and I said, watch this. And I lit a match, and thinking there would be a little puff, and there was a sustained flame. And I thought, I'm just going to leave this and see. The flame sustained for 3 full days. So there's huge amounts of methane coming out of these wetlands, even though they're taking in carbon dioxide. And methane is 23 times more potent than carbon dioxide as a greenhouse gas. So, right, looking at this, what gave me kind of an insider track, and publicly I would say in classes and elsewhere, oh yes, climate change is horrible, it's awful, we all have to do what we can to prevent climate change. And privately I was sort of snickering, thinking, yeah, no, probably not happening, but let's tell the people that it's happening, because the things that you do to solve climate change, that previous slide, are exactly the things that we need to do to solve more pressing problems. Stop burning coal, you won't have mercury in the atmosphere, right? Start doing sustainable agriculture, you're not deforesting the rainforest. So I was, sort of thinking, yeah, let's fool people into thinking climate change, it's scary. The reason for that is because I'm trained as a geologist, and I'm used to thinking not on the scale of 10 years or 5 years or even 100 years, but on millions of years or, in extreme cases, billions of years. And this behind me is a graph of climate change on Earth through time for about 1 million years, 900,000 years. Geologists have been really ingenious about reconstructing climate back through time. We look at lake sediments. We look, as you probably know, ice cores. I had a professor in graduate school who looked at fish ear bones. He would take fish ear bones out of the fossil record, and he would look at the stable isotopic concentration of oxygen, DeLo18, figure out what the climate was back then. We've actually even looked at vineyard records over in Europe, these old vineyards. You can look at how much wine was produced and back into what the climate was. So we've been quite ingenious about figuring out climate back through time. And we are 100% certain of this data. So if you look at this, again, there's present, right? You're being shown these graphs that essentially are a tiny piece of this, right? You see climate change. Oh gosh, look at the temperature's rising. But if you extrapolate back and you see over almost 1 million years, this is what global average temperature is doing. And we came along right around here with our Industrial Revolution. So was it the case that climate was perfectly stable and happy until we came along and then suddenly, And I kind of presented that to you last class. Is that what you're seeing here? We did it? Right, no, it's not. There are these cycles of glacial, interglacial, glacial, interglacial. And there's a guy by the name of Milankovitch that figured this out. He said, this is nothing to do with humans. This has to do with Earth's orbit. It's an astronomical phenomenon that we are assigning blame to humans for. So there are three things that Earth does in its orbit. Here's the sun. Earth goes around the sun. Sometimes the orbit is more elliptical, so it's farther away and then closer, farther away. And sometimes it's more circular. And what Milankovitch first said is that when it's more elliptical, then it will be colder on Earth. And so he tried to map out the elliptical versus orbital pattern that we know from cosmological data with this. And guess what he got? No agreement. So he said, all right, maybe it's a wobble. It's called precession. Earth wobbles in its orbit. And he said, well, the glacial periods are when the Earth wobbles away from the sun. Tried to figure that out, corroborated to this, nothing. So there's one more thing that it does, and it tilts. You know that it tilts anyway, that's the seasons, right? But sometimes the tilt is more extreme, and other times it's less extreme because of all the terrestrial landmass in the northern hemisphere. He said, well, when the tilt is more extreme, that's when there's an ice age. Also, no agreement. But he didn't give up, and he went to harmonic math, which means that you sort of add things together. And what he said is that sometimes the Earth's orbit is more elliptical, and it's also wobbling away from Earth, and it's also really tilty. And when those three things line up, you get an ice age. Sometimes the Earth's orbit is more circular, and it's wobbling towards the sun, and it's more tippy, or less tippy, rather. So that's when you have an interglacial period. When he did that, guess what he got? Perfect agreement, with two exceptions, two ice ages that weren't accounted for. One, 65 million years ago. Does that number ring a bell to anyone? The end of the Cretaceous? Dinosaurs all died. Massive meteorite strike. Plunged into global darkness. When you put that in there, you get an ice age. And then the end of the Permian. You have another ice age that was conclusively linked to a meteorite impact which caused global darkness. And species all died. When you put those two in, you have perfect agreement. So Milankovitch said, never mind, look at this. This is an astronomical phenomenon that we are thinking is us. So that is really kind of powerful evidence to the contrary of climate change. But now we have data that shows that if you continue the Milankovitch theory forward, we have diverged from the pattern, and we have diverged more rapidly than anyone could have thought. So it's ironic that this very theory, this very graph that people like myself use to say, climate change, whatever, is the basis for which we can then go to the other extreme and say, this is what should be happening. We geologists know what should be happening, and this is what's happening. If you saw Al Gore's movie, An Inconvenient Truth, right, he gets into a cherry picker and he goes up 2 stories to show the way the data diverged. So this is the reason, this is the data behind why people think climate change may not be real. But up to you to decide. So the last thing we're going to talk about somewhat briefly is ozone thinning. And ozone thinning, you may not need to write down or look at any of this at all because we talked about it last time and I showed you a graph of it. But just to remind you, ozone accumulated when PS stands for photosynthesis. Photosynthesis created the waste product of oxygen, which moved up into the atmosphere, the troposphere. Animals can breathe it. In the stratosphere, O2, the waste product, hit with ultraviolet radiation, breaks in two, and will group up with another O2 and make ozone. And it's up in the stratosphere, about 25 to 35 kilometers high. And we need this because it filters out the ionizing radiation that did not allow life to live in the presence of it. We came along with refrigerators. Remember all the things we talk about, the jets, space shuttle, fumigants for grain silos, the medical industry, propellants, refrigerants, all that stuff we talked about last time. This is all the stuff that came out. We fumigate ship cargo holds, etc. Using these chlorofluorocarbons and other ozone-depleting compounds caused the following. These things, again, were a dream. They were stable, colorless, odorless, tasteless, non-flammable, etc. So there's a lot of text on here, but I want you to focus on the picture. What happens is there is one of the many chlorofluorocarbon molecules. Down here in the troposphere, it's fine, does nothing. When it goes up into the stratosphere, it's hit by the sun, and ultraviolet radiation will strip off a chlorine atom. Nothing toxic about chlorine, right? Strips off a chlorine atom. The problem here is that chlorine, when it encounters ozone, it's energetically more efficient, it's chemically more stable to have, instead of ozone and one atomic chlorine atom, to have chlorine monoxide, ClO, and O2. Again, neither one of those are poisonous, toxic, right? Oxygen is the thing that makes ozone in the first place. So there you have chlorine monoxide. The problem there is that when you have monoxygen, remember these reactions are all going on in the upper atmosphere, so the sun's rays hit an oxygen that moved up there, split it. So you have monoxygen up in the atmosphere all the time. When chlorine monoxide is in contact with monoxygen, you cause O2 and you liberate the chlorine. So all you're doing is taking ozone and turning it into oxygen. But see, what you've done is you've liberated a chlorine atom that's free to come around and around and around. And I'll tell you about how many ozone molecules one chlorine atom can break down. And these things are up there, and this chain reaction nature of the breaking down of chlorine molecules or ozone molecules causes a big problem. One chlorine can break down over 100,000 ozone molecules. And so this is going on everywhere, all over the atmosphere. So what happened is, we developed these in the 30s. We put them into wide use in the 60s and 70s. In the 70s and 80s, we saw the problem. The problem was, in 1984, we noticed that ozone over Antarctica had declined by 50%. It's seasonally controlled, and I'll tell you about that in a bit. It's seasonally controlled. So I'll tell you about that later. Seasonally controlled, and it's spatially controlled. Just so you can see, this is 1956 to 1984. When we noticed it, we were using chlorofluorocarbons radically. 325, it's not down to 0, it's down to 175 here. But looking at the ozone and ozone holes, put these out, you can look at them. Ozone breaks down naturally, it forms oxygen. And these holes are in the southern hemisphere, which is kind of good, right? Because not a lot of people live in Antarctica. It's considered to be a serious long-term threat to humans and to many other animals, as well as to all the primary producers. I'll show you a list of what happens. So these chlorofluorocarbons are causing this depletion. And you can see here that if you had show you the next picture. If you had a good situation, you would have all red here. This is the southern hemisphere. You would have all red, and that means that ozone, as measured in Dobson units, we're going to work with Dobson units on Friday in class. It's, we'll look at it later. It's a measure of the gas. It would be all red. We don't have all red. If you get to green and yellow, somewhat compromised. Blue, very compromised. Purples and grays, essentially there's no ozone left. None at all. So you can see that we started looking at this in the winter. Things start to decline. And then it can rebound seasonally. Did I do that right? So the mechanism is such that in the winter in the southern hemisphere, convection currents in the atmosphere, convection currents in the atmosphere will bring the chlorofluorocarbons down to the bottom of the Earth, right, as we orient it. We talked about those convection cells that create weather. It's dark and it's cold, and so there are ice crystals that are there, and essentially the ice crystals, the chlorofluorocarbons sorb onto the ice crystals. And then when it turns spring and summer, the ice crystals melt because it warms up and releases the ozone that's been, the chlorofluorocarbons that have been accumulating, and they get set free and they destroy the ozone. So that's why there's a seasonal aspect to it. There's also a spatial aspect to it. Again, the convection cells we looked at when we were looking at weather bring the chlorofluorocarbons to the poles, to extremes. So I guess that's good for us, right? Because not a lot of people live in the Pacific Ocean in the southern hemisphere. Happens in the Arctic Circle as well. Not as much, only about 38% to the 50% that was in there, in the Antarctica. So sorry. I'm going to put these all out. And then, yeah, okay. So what happens? This is the part where you have to be very clear about the difference, at least for the purposes of our upcoming quiz. Very clear about the difference between effects of climate change and effects of ozone thinning. Happening in different areas, right, caused by different gases, and the effects are quite different. There's an increase in UVA and UVB, both rays, so an increase in this harmful ionizing radiation that we evolved in the absence of. So this is something that causes an increase in the incidence of skin cancer. We'll talk a little more about skin cancer in a minute, but malignant melanoma kills a quarter of all of its victims within 5 years, despite chemotherapy, surgery, and radiation. There are some skin cancers that not that you want to get them, but are more benign. Malignant melanoma is awful. 100,000 people in the United States die each year from this type of cancer, which is caused by increase in exposure to UVA, UVB rays. Tanning parlors, by the way, increase your chance of getting malignant melanoma by 50%. The highest rate of malignant melanoma, lest you think it's an old person's disease, is in young women. Antibiotics, birth control pills also increase your rate of getting malignant melanoma. So those are all things maybe to avoid, again, thinking about the skin cancer aspect. Here's an interesting side note as well. I used to, when talking about this, used to say, so wear sunscreen, wear sunscreen, wear sunscreen. The American Dermatological Association paired up with a bunch of other skin organizations to correlate the places where ozone thinning is the worst to the highest increase in skin cancer. And guess what they got? No agreement. So then they started trying to look at other things, and essentially the highest rate of skin cancer, including malignant melanoma, but also basal squamous cell carcinoma, happens in developed countries, and now they're more and more conclusively linking it to the sunscreen rather than the ultraviolet rays. Your skin is your largest external organ. It's semi-permeable. You absorb about 30% of whatever you put on your body into your blood, into your body, whether it's deodorant or moisturizer or whatever. So you take these huge amounts of these chemicals and you put them all over your whole body, and it's hot out, so you're perspiring, your pores are open, and you're absorbing the heck out of these chemicals. And it used to be, when I was younger, these things like zinc oxide and these chemicals that were long-lived. You could put on sunscreen once and be out all day and not get burned. But they only protected against UVA rays, right? And so people are still getting cancer. So now they're pushing through all these chemicals, Helioplex, Parsol, 1759, all these chemicals that are broad spectrum. So you sacrifice longevity. You guys have to put it on every 2 or 3 hours, right? For broad spectrum protection. Doesn't last very long, but it protects you more thoroughly. But they just got rammed through the FDA without a whole lot of testing. And so it may very well be that these sunscreens that you're supposed to be protecting yourself with are the things that are giving cancer. Again, it's not conclusive, but it's interesting data. Environmental Working Group puts out a cosmetics database. If you're someone who spends a lot of time in the sun, it's, look up cosmetics database. It's cool. You can type in whatever you want. It's nonprofit. There's no ads. It's just looking at toxicity studies. You can type in sunscreen, and it will tell you which ones are bad, which ones are good, and why they're bad and good. You can do it with anything, so neat. And if you use a lot of it, good to do. These days, the shirts that have, and the sun shirts that have UPF built into clothing is probably better to use because of the suspect nature of these sunscreens. Immune system effectiveness decreases. So people with HIV or with AIDS, people with compromised immune systems will really suffer, but all of us are going to get sicker. We are not evolved to deal with the presence of these ionizing radiation. Eye diseases and cataracts. Here's something kind of interesting. If you're going out in the summer and you have the choice of wearing cheap sunglasses or no sunglasses are actually better. The reason for this is because you need to have in the lenses full spectrum protection. Your eyes, especially if you have blue eyes, are super sensitive to ionizing radiation. And so if you go out into the sun, they used to be, again, when I was younger, we had these sort of John Lennon glasses and didn't do anything. Now you guys have these big, huge goggle-like glasses that lay flat on your face. That's fabulous because it doesn't let the rays in. Excellent. Keep that up. Keep that in style. But you have to have UVA, UVB protection because if you just have tinted lenses, what happens is your pupils dilate. You're telling your body it's dark out, but you're not protecting your retina and your eyes from the ionizing radiation, and so you will increase your chances of different eye cancers, of cataracts, of tumors, of things like that. So it's really important to have good sunglasses that have broad spectrum protection and wear them when you're outside. Plants, same thing. Plants have the equivalent of cancer, right? We have photosynthesis decline, mutations in crops, and reduced yield. When you combine the fact that climate change is causing plants and agriculture to shift northward, and ozone thinning is causing photosynthesis to decline, and our last situation, population increase, is causing there to be more people on Earth. Kind of tough. So that's the list of things. What are we doing? 1992, we had the Copenhagen Protocol, which strengthened the Montreal Protocol. This is something that we know is this is something that we know is going on, and we have been pretty effective at solving it. The Copenhagen Protocol and the Montreal Protocol, and 177 nations signed on, it is a serious situation, but we have been successful on the one hand in that we've reduced our use of ozone-depleting compounds by 90%. So we got rid of them. We changed what we've done. We've moved to different ways of doing things that don't use these. The rules are such that you have to move away from them unless there's no alternative. So for example, strawberries are really bad for the ozone layer because there's a fungus in strawberry fields, and use methyl bromide to fumigate it, to kill the fungus, and that is an ozone depleting compound. But we can't find anything else that kills that fungus besides methyl bromide, so we still use it. So we've been more successful, vastly more successful at ozone thinning problems than we have about climate change. So I guess that's good news, right? We have the potential to target these things and do it effectively. Kind of the bad news, though, is that with the chain reaction nature of ozone depletion, the ones that are still up there from the 70s, from the 80s, from the 90s are going to be causing a decline in ozone thinning until about 2065, when it will rebound in earnest. So still up there, still causing problems. So that's the situation with that. Yeah, I was going to start on population. I'll do a quick population before our lab, but I will gross you out because it's a good idea to look at this. So if you're squeamish, look away. So everybody loves a wonderful tan, right? But one bad burn can lead to the kind of cancer that you want to get, basal cell, squamous cell carcinoma. What the dermatological societies say is A, B, C, D. A, if you have anything on your body that is asymmetric, get it checked out. B, border. If the border is irregular, sort of bleeds into the surrounding skin, get it checked out. C, color. If the color changes or if it has sort of iridescent look, then you should get it checked out. D, diameter. If it's bigger than the head of a pencil eraser, you should get it checked out. So these are mostly basal. They're squamous cell carcinomas. So these are things that, obviously you should have checked out. There's a woman with a basal cell carcinoma on her nose, man with a squamous cell carcinoma on his knuckles. This is the kind of cancer you don't want to get. This is malignant melanoma. This is the stuff that kills a quarter of its victims in about 5 years. So there's a woman getting the malignant melanoma carved out of her back. And the last thing is, make sure you wear good sunglasses. Sorry, can't resist. So I'll see you.